Okay. Hello, everyone. Just making sure I'm on the first page. So these are video notes that you should watch before class because I'm not going to go back over this in class. I want to focus more on working through the problems, but I wanted to show you the background on how we solve linear differential equations. So far you all have learned how to solve separable equations, and that's all now, right? Besides doing the direction field. So this is solving linear equations. And let me say this, so you should definitely define the terms on the first page. Do that first, and once you do that, you will see how they define linear, and I'm going to define it sort of an alternative way to look at it that I think helps when you solve the linear equation. Okay, so the alternative definition of first order linear differential equation, a first order differential equation is linear if it can be written in the form dy over dt equals a of t times y plus b of t, where a of t and b of t are arbitrary functions of t. Okay. And so to solve a linear differential equation, as you can see, there's a lot going on, but the good thing is I want to show you the background of what we're doing. But once I show you the background, you won't have to repeat this. We'll just go into the methods. So when we get to class, we're going to start with the methods. But again, this stuff can become involved, and so I want to make sure that you all should be reading ahead in the book and not just waiting to come to class to see this for the first time, because we're going to keep moving. All right, so step 1. Okay, so to solve this first, and so notice that we're calling this expression 1, and so we rewrite 1 as dy over dt plus g of t y equals b of t, where g of t, so if you go back to 1, you sort of should know what g of t will be. It's going to be negative a of t. Okay, you all see that? We called it g of t. We just don't want to deal with the negatives. We just want to stick with the positives, sort of what we do with constants sometimes. Okay, so going back to Calc 1, and this class, if you haven't learned already, you'll see that Calc 1 and Calc 2, you need to make sure you're strong in the different techniques, derivatives, integration techniques, because it will be coming back in this class a lot. Okay, and so recall the product rule with functions, y of t and mu of t. Okay, and so the product rule you should remember is the derivative of the first times the second. So I'm going to write this as mu of t times dy of dt. Okay. And then plus the derivative of the second times the first. So plus y of t times d mu over dt. Okay. I just wrote it because I wanted the functions in front. If you want, you can write dy dt times mu of t, but just wanted to make sure it's clear. Okay. Now step 2, so that's step 1, is to look at the product rule. Step 2 is to multiply both sides of 1 by mu of t. Okay. And if we do that, okay, so we're going back to 1. And so that's how we get the mu of t times dy of dt plus, we're going back to, I should have called it differently. We're looking actually at this one. So multiply, let's call this star. So multiply both sides of star by mu of t to get mu of t times dy of dt over dt plus mu of t times gt of y equals mu of t times b of t. Okay, so that's pretty straightforward. And let me say this. So the book also shows you this. It does it differently. And I think this way algebraically makes more sense, and technique wise it sort of makes more sense. In both, we're going to have to assume something. You'll see in a minute. Actually, in the next line, we're going to assume something is true and then make conclusions from that. And that's going to help us to figure this out. Okay, so we're actually assuming, so now we're on this line here. If we assume that, let's say we found this mu of t function, right? So let's say we found this mu of t that satisfies this expression here, that the derivative of y of t times mu of t over dt equals mu of t dy dt plus mu of t times g of ty. So again, this is something we're assuming. This isn't necessarily something that flows from what we just did. This is something we're assuming. Okay, and so if we assume this part here, let me not call it star. So if we assume this, then we can say that d of y of t times mu of t, so again, looking at sort of that product rule, we can say that equals mu of t times b of t, right? And that's all we're doing is substituting in, instead of writing this, we're substituting in that. Okay, so that's all we did there. And we're going to call that expression 2. Okay. So the next step is we're going to integrate both sides of 2. So we're going to take the integral of d of y of t times mu of t. You see that mu of t over d of t equals the integral of mu of t b of t dt. Okay, so hence y of t. So remember, the integral of the derivative is just going to be whatever that expression is there, right? So that left-hand side simplifies to y of t times mu of t, and it equals the integral of mu of t, b of t, d of t. So then just divide both sides by mu of t, and y of t will equal 1 over mu of t times the integral of mu of t times b of t dt. Okay? No, remember, we are assuming. So again, we are assuming that we found this function mu of t. Okay. Recall, so we need to find what mu of t is. We need to figure out what mu of t will be. Okay. That's the key in solving linear differential equations. We're doing all this to find this function mu of t, which will help simplify our lives and give us this y of t. Okay, and so we need to find mu of t. So recall again that because of what we assumed on that last slide, that the derivative of y of t times mu of t over dt equals mu of t times dy dt plus d mu of dt times y of t. And I should have reversed that, but it's fine. And also recall that we said that the derivative of y of t times mu of t over d of t equals mu of t times dy dt plus mu of t times g of ty. Okay, so again, we assume, and this is the one we assume. Well, you see, we can set 3 and 4 equal to each other, right? Okay, so if we set 3 and 4 equal to each other, we're going to get mu of t dy over dt plus d mu over dt times y of t equals mu of t dy over dt plus mu of t g of t y of t. Okay, and now from here, thus, what can we do? Well, we can cancel, right? These two cancel. And so we're left with d mu over dt times y of t equals mu of t, g of t, y of t. Okay, so d mu, and you guys see why I wanted to do this before class and not in class. This will take the whole class period, right? To break down and understand, but I should be done by 15 minutes. Okay, so d mu over dt equals, if we divide by y of t on both sides, mu of t times g of t. Okay, hence g of t equals 1 over mu of t times d mu over dt. Actually, hold on. I want to put it the other way. So hence, it doesn't matter, but I'll do it the other way, like it's in my notes. Mu of t equals, mu of t times d mu over dt equals g of t, right? Okay. So we can integrate both sides. Well, actually, then we can multiply both sides by dt, right? So it looks like sort of like our separable equations, correct? So we'll have d mu over mu of t equals g of t d of t. Thus, integrate both sides. D mu over mu of t equals the integral of g of t dt. Okay. And I think I have room over here. Let's see. So on the left-hand side, what will we get? Well, we're going to get the natural log of the absolute value of mu of t equals the integral of g of t times d of t. Okay. And we're trying to solve for mu of t. Remember, that's our goal. We're trying to find mu of t, okay, in case we forgot on this journey. But we take e to both sides, right? So e raised to the natural log of mu of t equals e to the integral of g of t d of t, okay? And so on the left-hand side, we know this simplifies to the absolute value of mu of t equals e to the integral of g of t d of t. And mu of t equals e times the integral of g of t dt. And this is because, I'm going to need another slide. So here's this note, because I know you may be wondering, well, where did this absolute value go? All right, and so the note we can make is this. We only need, mu of t is called an integrating factor. Okay, and you should have that in your definitions from page 1. We only need one integrating factor. Mu of t to solve. So just assume our constant is 0. All right. And so this is why we can drop the absolute value. It's a little more, I'll talk more about it when we do an example, because it makes more sense. Hopefully it should make more sense when we do an actual example, so you can see why we're okay with dropping that absolute value. But we just found our integrating factor. So our integrating factor mu of t is equal to e to the integral of g of t dt. And let me just say here that you should have seen, this is still page 2, but this is the beginning of page 3 in your notes. All right, and so this should all be on page 3, and then you should see that summary at the end of your notes. And what we're going to do, so it's a 4-step process. The first, here's the thing, you want to make your life simple. So if this is a separable equation, then proceed as usual. Now, what we'll probably do in class is do some examples where we will solve it as separable and solve it as linear, just so you can see you have different techniques you could use, just like in Calc 2 and Calc 1, right? But the summary on page 3 at the bottom says you decide if it's separable equation and proceed as usual. Because if it's separable, you all know how to solve it and just go that way. Step 1 is to find an explicit solution to a linear differential equation. You have to write it in that form, dy over dt. This is in your notes. You don't have to write this down. Plus g of t times y equals b of t. So if it's not in that form, you get it in that form first, because you're going to need to know exactly what that g of t or whatever your independent variable is. It could be x, whatever. You need to know what that is. And then in step 2, you need to compute the integrating factor, which is e to the integral of g of t dt. That's why you need to find out what your g of t is. And then multiply both sides of the linear differential equation by mu of t and integrate. We're going to have some fun in class. So I'm excited about this, but make sure you go back over it and just understand the algebra behind it and sort of the process, and you will see how we're going to apply it in class. Under 15 minutes, I am done.